solve those. You can do it without a graphing calculator. However, you'll probably see in this lesson that using a graphing calculator can save you a lot of time. Okay, so when we're asked to solve a polynomial function or find the zeros for it, in the past we had quadratic functions, which were fairly simple because we could either factor it to solve or we could use the quadratic formula. However, we now have functions like this here. It's a fourth degree, which we do not know how to factor necessarily, so we have to find a different way to find the zeros of the polynomial since we're unable to factor that. One way to find the possible rational zeros, because we found that when we do, in the last lesson, when we do synthetic division, we can find zeros by doing synthetic division. If their remainder is 0, then they're one of our zeros, and we can use that to break down the polynomial. However, there are lots of real numbers, and it would take us forever to test every real number. So here we have what's called the rational zeros theorem. Okay, this is how you find the possible rational zeros. Now, there may be other real zeros that don't show up here, but this gives us somewhere to start from at least. So that rather than having to test every single real number, we have a group of rational numbers that are possibilities for the answer. It doesn't mean they will be the answer. Maybe none of them are zeros, but most of the time at least one of them is. It gives us a place to start from. It gives us a smaller group of numbers to choose from and test in when we're doing our synthetic division. Okay, this is the rational zeros theorem. It says that if you have a polynomial like we do here, all of the coefficients or numbers in front of the x's have to be integers, which means they have to be whole numbers. You cannot have fractions there or decimals there for this to work. Okay. It says what we do is we put p over q, where p is the factors of our constant and q are the factors of our coefficient. Okay, so we are going to be putting the factors of 5 over the factors of 2, and we want to leave the possibility of the positive and the negative. So here's how we form our possible rational zeros. The factors of 5 are 5 and 1. Only factors are numbers that multiply to equal it. So 5 and 1, that's the only way you can get 5 using multiplication. On the bottom, we put the factors of our leading coefficient, which is 2 in this case. Factors of 2 are just 1 and 2. And then we have to do each possible combination of these. So you just go one at a time. So I would look at the first two. 5 over 2 is one of my possible zeros. And then I put 5 over 1. Okay, or 5. And then I go to the 1. I'm going to do this one in green so we can separate. And I go 1 over 2 and 1 over 1. Okay, so I've done each possible division. I'm going to reduce any that can be reduced. It looks like my possible rational zeros are positive and negative 5 halves, positive and negative 5, positive negative 1 half, and positive negative 1. Which this is awesome because instead of just having to guess numbers and check them to see if they're zeros, we now have a smaller group to check. So these are the possible rational zeros. And now we're down to a group of 8 numbers to check instead of an infinite number. Okay? So that is why we like the rational zeros theorem. Let's do this next one. So again, to check for rational zeros, you do the factors of the constant, or that number on the end without an x on it. Won't necessarily be on the end, but it's the number without a variable next to it. So factors of 6, 6 times 1 is 6, and 2 times 3 is 6. So 6, 3, 2, and 1 are the factors of 6. Our leading coefficient, its factors go on the bottom. The leading coefficient is 1, so we just have plus or minus 1. We would write out each combination, but we're dividing by 1 every time. So our possible zeros are positive or negative 6, 3, 2, and 1. And like I said, at least this breaks it down to just 8 possibilities instead of an infinite number of possibilities for us to check. And again, it's important to know that these are the possible zeros. They don't have to work. It also is important to note that they're the rational zeros. So there could be other real numbers, like 3, the square root of 3 is not a rational number, but it could still be a 0, okay? But this, again, the purpose of this is to give us somewhere to start from to break down our polynomial. And let's do this last one here. So again, we want to write the possible rational zeros. So we put the factors of the constant term, 10. Its factors are 10 and 5 and 2 and 1. Those are all the numbers that will divide evenly into 10. Over the factors of 17. 17 and 1 are my only options there. So now let's write out all of those possibilities. So you take the 10 and you put it over the 17 and over the 1. And then we move to the 5 and do the same thing. So we have plus or minus 10 17, plus or minus 10, plus or minus 5 17, plus or minus 5, plus or minus 2 17, plus or minus 2, plus or minus 1 17th, and plus or minus 1. Okay, so that has us down to 16 possibilities to check. Breaks it down a little bit, and this would give us a starting point. Okay, so if we were not using a graphing calculator, this is where we would start from. Okay, on your assignment you will be asked to do a few of these. That's why I went ahead and did the rational zeros theorem. And now, the rational zeros theorem. And now we're going to talk about why using a graphing calculator gives us a huge advantage. Okay, so some of your questions